time interval. It's like we take a little snapshot of the reaction. So we start off with all reactants. Notice that I know I'm at equilibrium when my concentrations of A and B and level out. And so there's our equilibrium point right there. That's when we reach equilibrium. We're talking about equilibrium, and first I need to define a reversible reaction. I have a reaction here, and it's just what you think. It goes both ways. Think about things that are reversible. You can go one way and then you can go back the other way. So the way we recognize a reversible reaction is that right there. Notice the arrow doesn't just go to the right, to the product side. It's also going back to the reactant side. So in a reversible reaction, both reactions occur at the same time. What we would call the forward reaction, that would be in this direction, and then the reverse reaction is going on at the same time. So some particles in this reaction are coming together and bonding, and some are breaking apart. So let me describe what equilibrium is, and you probably have a pretty good idea because we use that word in everyday language as well. But the definition that you need to memorize, for real, you need to memorize this one, is this. It is when the forward rate equals the reverse rate. So the rate at which a reaction is going forward is equal to the rate it's returning. So I want to give you just a little example that I like to use in my classroom. It's involving the mall. So let's say the mall opens and we have some people going in. So this is the rate at which people are going in. So here they go. Have a couple people in the mall. After 15 minutes, nobody's leaving yet, right? So it's still more people are coming in. And so we're getting more people in the mall. And then at some point, people are beginning to leave the mall. They've done their business and they're leaving, and there's still a few people in the mall. And then at some point, the rate at which people go in is equal to the rate at which people come out. And so people are continuously going in and they're going out. And we know that when that rate is equal, we have equilibrium. And so at this point in this model, I would say we've reached equilibrium. Now, individuals are still going in and out, but the rate at which people are going in is equal to the rate at which people are coming out. So let's carry that over into a chemical reaction. So here I have a very simple reaction of A and B. So A is going to B. So we start off, let's say we're at, well, let's put some times on here. So this is T0, and we'll call this T1, T2, and T3, some time interval. It's like we take a little snapshot of the reaction. So we start off with all reactants. It makes total sense. So here I have, I'm counting those, I have 8 A's, reactants. And then in the next box I have, let's see, I think I have 6 A's, and then it's coming down, I've got 3, and then I've got 3. Now let me count up my blues. Here I have 0 blues, and then I have 2 blues, and let's see, that would be 5 blues and 5 blues again. Okay, and so it makes sense that the A's, we're reducing that number, and then the B's are coming up. So when does this reach equilibrium? Well, it's right here. This is what we would call equilibrium. Notice that I know I'm at equilibrium when my concentrations of A and B don't change. Okay, I didn't say that A and B are equal because I definitely have more B, but the concentrations are the same. So that's when I'm at equilibrium. Now let's look at a graph that you're going to need to be able to interpret that. So the first graph is the reaction rate. So I'm going to show you that right there. So the rate, and it's typically in, well, this one is moles per second. Okay, so the rate at which it's occurring. The forward reaction starts off really high because that's all we have is reactant, and it's going to go slower and slower and then level out. The product, or the reverse reaction, well, there is no reverse reaction at the beginning because we have no product, but it will pick up as we make product and level out. And so there's our equilibrium point right there. That's when we reach equilibrium. Now, the other way to look at it, and I think this one makes a little bit more sense, is concentration. Okay, we started off with a whole bunch of A, a big high concentration, and it dropped, right? And then we started off with no B, and its concentration came up. So this is my B and this is my A. Okay, and then again, equilibrium is when the concentrations are constant. You can see it in both ways. When the rates match, like absolutely match, and the concentrations are constant. Okay, so let's take a look at our reaction. Let's see if you could actually draw this. So my reaction of A and B. We start off, remember, with a very high forward rate, and it's going to come down. Our reverse rate, we started at 0. That reverse rate was, remember, B going to A, and it's going to come up like this. So when those two things meet, that right there is our equilibrium. Remember the definition. When the forward rate, and that's what this one is, the rate forward, I'll call it rate forward, and the rate reverse are equal. And look where they matched up, right there at the equilibrium point. Okay, can you draw the concentrations? Well, we started off with a whole bunch of A, and then here's my B down here. We had no B to start with. So what does my concentration look like? Well, A, we had a lot, and we lost it pretty quickly, and then it leveled out. B started off with a very little bit, and then it came up to, do you remember that one? Like that, okay? And the point at which they were constant, those concentrations, is equilibrium. So could you look at a graph of either concentration or rate and decide where and when the reaction reached equilibrium? And if there were time units down here, you would say that was at 42 seconds or whatever that time interval was. I hope that helps you understand reaction rates of reversible reactions.